Let's have a look at reading PPM signal using Arduino. In this example, I will use a simple 2-channel PPM signal. I will start by defining my axes. Here I will use time on the x-axis and voltage on the y-axis. This image shows the waveform a PPM signal takes when both channel 1 and channel 2 are set to maximum value, which is 2000 microseconds. I can now label a few points on this image. I will pick out the rising pulses and I will label them A, B, and C. Since on the x-axis I have time value, these 3 points A, B, and C actually represent different timestamps. So if you wanted to calculate the value of channel 1, you will simply take the timestamp B and take away the timestamp A from it, and you'll get channel 1. The same you can do for channel 2, but this time you will have the channel C first, and then you will take away the timestamp at B. The same thing can actually be done on the falling pulses as well. Instead of rising, you'll have the same positions A, B, and C. And then to calculate channel 1, you'll have B minus A, and channel 2, C minus B. And the exact same thing happens when we look at the stick position set to their minimum value, which represents 1000 microseconds. So it doesn't matter if you use a rising pulse or a falling pulse. You can use the same mechanics behind to calculate the value of that particular channel. Now, to calculate the channels, we will need to use interrupts. In particular, we will use a pin change interrupt. Again, I have the waveform of the PPM signal, and if I connect this waveform to an interrupt pin, I will have interrupts occurring at all of these positions. Due to the nature of the signal, we only need interrupts at either the rising or the falling position of the signal. In this example, I will use the rising pulses. Now we know how channel 1 and channel 2 are transmitted in the signal, but in fact there is actually a third channel. I will call this channel channel 0 because this is not a real channel. This channel defines either the end or the start of the data stream, and after that our signal continues. The way we measure this is by using these following steps. First, we will wait for interrupt, and when the interrupt occurs, we will record the timestamp, and I will call it timestamp 0. Then we're going to wait for the second interrupt and do the same, record the timestamp 1. At this time, we're also going to set the channel 1 as the difference between the two timestamps. Then we're going to wait for the third interrupt, and when the interrupt occurs, record the timestamp and set the channel 2 as the time difference between timestamp 2 and 1. Then we're going to wait for the fourth interrupt, and we're going to set the channel 0 as time difference between timestamp 3 and 2. And after that, we are going to go back to step 2. This is because the interrupt number 4 is exactly the same as interrupt number 1 because the signal is repeating. Now, when writing the code, we first need to enable the interrupts. This first line here will enable the interrupts in the Arduino system, and the second line here will tell the Arduino that the PC int 0 is the pin that the interrupts will occur at. This pin would represent to pin 53 on the Mega board and pin 8 on the ONU board. We can now use a pointer to refer to the part of the code which will run when the interrupt occurs. What we need to do now is pick either the rising pulses or the falling pulses. This can be done using a simple if command, and inside the if condition, what we can write is this condition here. This condition is the same thing as writing digital read high on this PC int 0 pin, but this line would take a lot less CPU cycles, hence the result will be a lot quicker. Before I can go any further, I need to define a few variables. The first variable is unsigned long. This will be used for 3 different channels, and the second is the timer. And then we're going to use an integer to count which pulse is coming at which time. To get the timestamp at each interrupt, I can use tpulse equals to microsecond. What this will do is take the system time using the microsecond function and set it to the array as tpulse. Next, I'm going to use a switch case to run different code for different pulse. This will take in the value of pulse. If the pulse is 1, it will run the code between case 1 and this break line. If the pulse value is 2, it will run the code between case 2 and break line. Same goes for case 3 and 4. And if the pulse value is not 1, 2, 3, or 4, it will straight away go to the default code, and any code written between default and break line, it will run that code. Since I have initialized the integer pulse to be 0, when the first interrupt occurs, T0 will become microsecond. In other words, T0 is the current timestamp. But when the program goes into the switch case, there is no condition for case 0. But we need to increment the pulse. Therefore, under the default code, I will write pulse plus plus. This will add 1 to the value of the pulse. Now, when the second interrupt occurs, this T1 will become the timestamp, and the case 1 will be launched. At this point, I can calculate the value of channel 1 by writing this line. This will set the channel 1 to be equal to timestamp 1 minus timestamp 0. And once that is done, I also need to increment the pulse. The same can be done for channel 2 and channel 0. There is, however, a problem with this code. We will use the same waveform again, and we expect the interrupts to occur at these points. Since Arduino takes some time to start, it can happen that while Arduino is booting up, it can miss one of the pulses. Now the Arduino thinks that channel 2 is channel 1, channel 0 is channel 2, and channel 1 is channel 0. This is a synchronization problem. And to fix this, what we need to do is whenever we calculate a channel value, we have to make sure if the channel value is greater than 3000, we set the T0 as the last pulse detected and set the next pulse equal to 1. This will make sure whenever we detect the channel 0, we reset our pulse number. In terms of the code, just after we've calculated the channel value, below we're going to write an if condition. And this if condition states that if the channel value is greater than 3000, then we set the timer 0 as the current timer, and we set the pulse value to be equal to 1. So when the next time the program runs, we are measuring pulse 1. We will also need a similar if condition for case 2 and case 3. This will make sure that if our channel 1 becomes channel 0, we will reset and resync. If channel 2 becomes channel 0, we will then reset and resync. If channel 3 becomes channel 0, we will reset and resync again. And for 2-channel case, I don't need this case 4, so I'll just remove that. You can use the same method to extend the code to read any number of channels. I have written the code here for 6 channels, and I've also added a serial communication in this code, and I'm printing all the data every 1/10 of a second using this print command here. To test my code, I will use this FlySky 6-channel receiver that has PPM output on channel 1. You may also want to make sure that your transmitter is actually set so that PPM data will be produced. And when we upload the code, we can see that we're starting to get some data in the serial monitor. Changing the channel 1 stick changes the value in the serial window. The minimum is 1000, maximum is 2000. Same as channel 2, lower the channel 2 stick and then the channel 2 lowers and goes maximum to 2000. Channel 3 also works. So does channel 4, channel 5, and channel 6. And for convenience, I will add this code in the video description. Thank you.